All right, you guys, so this is going to be second to last video. We're going to hit the in C naught part of 817. So the theorem's going to go basically the same. We just swap out the uniform norm and or the P norm to uniform norm. We swap out one of our propositions, and then we obviously change LP to C0. So now we're going to let F be in C0 with epsilon greater than 0. Then we know that there exists a G in CC, again, with the G arbitrarily close to F with respect to the uniform norm. And the reason that we know that this G exists is now by proposition 4.35, which tells us that since Rn is locally compact Hausdorff, C0 is the closure of CC, which means that we can always get arbitrarily close. Now, we say if I have phi in CC infinity, C infinity C, such that its integral is 1, we have, and we know that such function exists again because of the discussion during 8.1, then by, again, these two give us that this guy lives inside of here because G is still in CC. So now what we have is that the difference between these guys, and this I made the mistake in the last video, I was missing the second G. This thing is not going to 0 with respect to, this thing's norm is not going to 0. This thing is going to G because the integral is 1, and theorem 814 tells us that the convolution of this guy as t goes down to 0 is going to send this the convolution to the product of the value of the integral of phi and G. So this thing, because the integral of phi is 1, is going to G, so then the difference between these two is going to 0. And this is going to be in the uniform norm because obviously the difference, since this guy is getting arbitrarily close to Z, the difference between them is going to end up down. So what we get is that this is for sufficiently small c, that this guy is going to G, but G is in C, which is being closed, or which has closure of C0 and hence is dense. So then we get that C infinity C is dense in C0 as desired. So that gives us that finishes up the proof. I will see you guys in the next video, hopefully the last one for 818. I think I can do it.